Hi, the image that you see in front of you is one of the most famous images in astronomy. When image was made back in the 1990s, it was the deepest and most sensitive image of the sky that had ever been made. The image was made as a result of the director of the Hubble Space Telescope, Bob Williams. Now, Bob got sick of astronomers frittering away observing time on small projects, and he decided to use a huge amount of the time on the Hubble to observe a tiny bit of sky, and that became the Hubble Deep Field. The Hubble Deep Field is a tiny bit of sky, but it contains about 1,000 galaxies. And this image actually illustrates some of the things I do in my life as an astronomer. There's roughly 1,000 galaxies present in this image, and some of the brighter galaxies are fairly close by, but the more distant galaxies are so far away that light has been traveling to us for billions of years. And what that means is we're actually effectively looking back in time. Now, in fact, the most distant galaxy on the image is about 12 billion light years away, which means that we're looking 12 billion years back in time. Now, this ability to look back in time gives me, as an astronomer that's really interested in writing a history of galaxies, in trying to understand how galaxies formed in the first place and how they've changed over time, it gives me a huge advantage over real historians and archaeologists. As it happens, on my desk, I've got these fossils. And I bought these fossils in an antique shop in Cambridge for about £70. And if the person was telling me, was not lying to me, these are two ammonites, which were around in the Earth's oceans about 160 million years ago. Now, anyone trying to understand the history of life on Earth has to work with material like this, the kind of debris and the artifacts that are left over. However, as an astronomer interested in the history of galaxies, I can actually look back in time and see what galaxies look like. Now, Hubble was a revolutionary telescope because it was in space, but otherwise it was pretty much a traditional optical telescope. And to answer some fundamental questions about how galaxies formed, we have to go outside the usual visible waveband and go to other wavebands. And I'm going to tell you now about one big mystery that was around in the 1990s, and our observations in the sub-millimetre waveband, which is what I used much of my time, actually solved this big mystery. So the big mystery was about these guys here. This is an optical picture again, but this time it's an optical picture of a nearby cluster of galaxies, and the galaxies you can see in this picture are elliptical galaxies. Elliptical galaxies are kind of a little bit boring visually. They don't have the pretty spiral arms of our galaxy. An elliptical galaxy is basically a big pile of old stars. And the fact that all the stars in elliptical galaxies are so old, in the 1990s, it created a big mystery. Now, the reason for the mystery is because all those old stars must have formed at some time in the past. And when astronomers estimated the ages of the stars of the stellar populations of elliptical galaxies, they typically came up with about 12 billion years. And what that means is that 12 billion years ago, stars should have been forming at a very, very fast rate in elliptical galaxies. And when stars form at such a fast rate, it means the galaxy is going to be incredibly luminous. And so astronomers expected that if they looked out far enough out in space, which is going back in time, they should be able to see these incredibly luminous galaxies, which we call proto-ellipticals. But when they looked, they didn't see them. Now, they suspected the answer to that mystery was interstellar dust. Interstellar dust, tiny solid fragments of material in interstellar space, and interstellar dust acts a bit like smoke. It hides and absorbs the optical light from galaxies. And people thought, well, maybe these proto-ellipticals are just so full of dust, you can't see them at visual wavelengths. But then there was a real possibility that we could actually still detect these things by making observations at sub-millimetre wavelengths. Now, to give you an example of a sub-millimetre observations, I've got a couple of pictures here. On the left, you see an optical picture of the nearest galaxy to our own, the Andromeda galaxy. It's a visible picture. And on the right, you see a sub-millimetre picture. Sub-millimetre radiation, it's still electromagnetic radiation, but it has a much, much longer wavelength. And what happens is the dust grains that absorb the optical light, they get heated very slightly by the energy in the photons of light. They get warmed to 10 to 20 degrees above absolute zero, and then they emit sub-millimetre radiation. And back in the 90s, astronomers thought, well, if we do deep sub-millimetre images, we might start to see these proto-ellipticals. We might see the emission from the dust, the sub-millimetre emission from the dust that's absorbing all the optical light. The big problem, though, was that sub-millimetre astronomy at the time was still in a very primitive state. As you may know, the first time astronomers used a telescope in the visible waveband was back in 1609, when Galileo used one of the first telescopes to discover the moons of Jupiter, see the phase of Venus. First sub-millimetre telescope was only commissioned in 1987. And this photograph shows you that telescope. It's the James Clerk Maxwell telescope. It was built by the UK and the Netherlands as a minor partner. But it's actually not even it's even more primitive than that, because at the time in the 80s, there was no such thing as a sub-millimetre camera. And then in the mid-1990s, we suddenly got the world's first sub-millimetre camera, which was built by a team of UK scientists, some of whom are now in Cardiff. And suddenly we had the possibility of taking the first deep sub-millimetre pictures of the sky. What do you do when you have a new camera in a new waveband? You use it to point at the most famous bits of sky. One of those was a Hubble Deep Field. So a team of British astronomers took a sub-millimetre image of the Hubble Deep Field. And that's what they got. Now on the left again, you see the visible picture, the genuine Hubble Deep Field. Iconic picture. It's on most astronomers' walls. A beautiful picture containing about 1,000 galaxies. On the right, you see the sub-millimetre image. Now, most of this stuff you see in this sub-millimetre image is just noise. There's only 5 sources that have actually been detected here. But these sources contain, the discovery of these sources revealed a fundamental truth about the universe. The first thing about this image that's amazingly interesting is that if you go to the position of the brightest sub-millimetre source in this image, and then go to the Hubble Deep Field, which was then, remember, the deepest optical picture that had ever been taken of the universe, there is nothing on the optical position at the position of the bright sub-millimetre source. This is a galaxy that is so completely shrouded in dust that you can't see it, even on the deepest optical picture that has ever been taken of the universe, which is an amazing thing. Second amazing thing is the total energy being radiated by these 5 sources on the sub-millimetre image is roughly the same as the total energy being radiated by all 1,000 objects on the Hubble Deep Field. Now, we've done loads of observations of these things since, and we now know that what we're seeing on the sub-millimetre image are galaxies 10 to 12 billion years back in time, incredibly luminous, so they're forming stars at a rate roughly 1,000 times greater than our own galaxy. And these things have all the properties that we expected for proto-ellipticals. So this scuba survey, this survey with this first sub-millimetre camera, basically solved the mystery of the missing elliptical galaxies. So now, I said sub-millimetre astronomy was very primitive. It's been accelerating in its developments. If we move forward 10 years, we had the launch in 2009 of the Herschel Space Observatory. I was the co-leader of the biggest survey with Herschel. A team based in Cardiff built Herschel's main camera. And what you see now is one of the first images that my survey actually took. It actually doesn't look particularly exciting because there are so many sources on this image, you can't even see them properly. There's 6,000 sources on this image, so compare that with the 5 sources on the first sub-millimetre image I showed you. And there's so many you can't see them, so what I've shown here are blow-ups of 5 of the sources. Now, any survey in the new waveband always makes big discoveries, and I'm just going to share with you one discovery that we made, and the discovery was based on the 5 sources you see here. Now, these 5 sources were kind of interesting because for various reasons, we were pretty sure we were looking a long way back in time, sort of 10 to 12 billion years. But when we looked on an optical image, we found there was a bright galaxy at the position of each source. And these images actually show you what we think was happening. You look first on the 2 images on the left. On the far left, you see the sub-millimetre source again. This source is called SDP81, which has no great significance. I think it was the 81st source in one of our lists. SDP stands for Science Demonstration Phase. So you see this little sub-millimetre blob. The Herschel image actually shows no detail because Herschel was great at detecting things, but it didn't show a lot of detail. On the right-hand side, you see a combination of an optical image made with the Keck telescope in Hawaii and another sub-millimetre image. The optical light is shown in blue, and you can see, as I said, there's a big bright galaxy bang on the position of the Herschel source. Now, we managed to see a lot of detail in the Herschel source in the sub-millimetre emission by using a telescope called an interferometer to observe the sub-millimetre radiation. And that is shown, the sub-millimetre radiation is now shown in red. And the first thing you can see is that the sub-millimetre source is not coincident with the optical source. So the sub-millimetre radiation is not coming from the optical galaxy. Instead, it seems to be wrapping itself around the optical galaxy. And to see how that is happening, if you now look on the picture at the bottom, what we think is happening is a phenomenon called gravitational lensing. We think the galaxy that you can see in the optical image is a big massive galaxy, and the gravitational field of that big galaxy is bending the light from the distant sub-millimetre emitting galaxy around it. So if you imagine standing right at the right-hand side of the picture, you can see a little image of Herschel there. You're looking out into the universe. There's this nearby galaxy. The sub-millimetre radiation from the distant galaxy is being bent around it. And then when you look out in the universe, you look along the path of the sub-millimetre radiation, and you see the sub-millimetre radiation spread around the optical galaxy. Now, the discovery of these gravitational lenses was incredibly good news, because a gravitational lens essentially is a huge magnifying glass that allows you to see detail in any observation of the distant universe. And a few years after Herschel, we got yet another advanced sub-millimetre telescope, and this is a telescope called the Atacama Large Millimetre Array. It's an interferometer again. It allows you to see detail, and it consists of 65 dishes linked together at 5,000 meters height in the Atacama Desert in Chile. And this is what we saw with it when we observed SDP81. The picture on the left shows the ALMA image, and you can see this amazing ring, huge amount of detail. This is a thing called an Einstein ring. This is a sub-millimetre image, so you can no longer see the galaxy that's in the middle, because the lensing galaxy is not actually emitting any sub-millimetre radiation. The only reason we know it's there is because of the gravitational effect from the on the radiation from the galaxy behind. Now, by itself, the Einstein ring is amazingly beautiful, but it doesn't actually tell us anything about the distant universe because of the huge distortion on the emission from the very, very distant object. But what you can do is you can correct for the distortion. And when we corrected for the distortion, we got the image on the right. Now, this image is an amazingly detailed image. We're actually seeing as much detail here in a galaxy 12 billion years back in the past as we do when we used Herschel to observe the nearby Andromeda galaxy. So it's amazing detail, exquisite detail. And the detail is partly a result of the detail that you see with ALMA, but also on top of that, you have the magnification provided by the gravitational lens. So you see an exquisite image. And of course, the image looks nothing like the galaxies we see around us today. There are no spiral arms, typical of spiral galaxies. It doesn't look like an elliptical galaxy. Instead, you see a series of big clumps. These big clumps are big clumps of gas and dust. And by observing this galaxy in a variety of ways, we've shown there was actually a spinning disk here, which is actually rather like our own galaxy, but the disk is unstable and is in the state of collapse. And as the gas and dust collapses, it forms these big clumps, and then these big clumps, loads of stars form in these things, and you get the huge star formation rates that we see at this time. So this is actually effectively the first detailed image of a galaxy in the process of formation. So we're watching this galaxy as it forms. And so that's the kind of research I do. We're continuing to do more observations of ALMA. Next year, we hope to use the James Webb Space Telescope. And although we haven't yet answered the question of how galaxies form, observations like this are making major steps towards answering this question.